All right, homework out. Books open to page 220. You did, page 220 to 221. Numbers 35 to 42. And number 35 and 36, you were simply supposed to determine will there be vertical translation, horizontal translation, vertical reflection, vertical stretch, or vertical compression. And number 35, what is the only thing happening to our parabola here? Abby?
Horizontal shift.
Horizontal shift, how, where, what? That could be a lot of different things, right?
Wait, what?
Number 35, page 220 is where we should be.
Okay. Horizontal shift this way, one.
Which way?
This way.
Backwards.
Backwards one or left one. Good. Number 36, there are two things that we have to do to our parabola. And Audrey, what are we doing?
You're vertically shifting and stretching.
Okay, we're vertically shifting how, where, what? Because again, there's a lot of ways you can vertically shift, but what exactly are we doing?
You go up to.
Up to, there we go. That's the kind of vertical shift we're looking for. And then you said the other thing?
Stretch.
We are? We're not actually stretching. We're compressing. We are compressing because look at the A value. It's a 1/2, so we're shrinking everything to half size. All right, questions on questions on 36. Okay, number 37. We want to convert to the standard graphing form and graph. Number 37, they gave us f of x is equal to x squared negative 2x negative 6. What is this in the parabolic form? Let's come to Genesis. In the standard graphing form. What did you have for your answer on number 37?
I put it on the parentheses.
Right.
Oh, x minus.
What was your answer?
Oh, x minus 1 squared minus 7.
There we go. X minus 1 squared minus 7. That's what we were looking for. Good. And when we go to graph this, and for sake of time, I'm not going to do the detailed graph, but when we go to graph this, what are the only changes we're making to our parabola here, Genesis?
We're going to start at -7 and go to -1.
Maddie? We're going to go down 7, but we're going to go forward 1. Remember, whatever's in the parentheses, we've got to think opposite. So we're going to go down 7, forward 1. So we'll be here at 1, -7. And then it's just, over 1 up 1, over 1 up 3, over 1 up 5. And so we'll get a parabola that looks something like this. Again, this is just kind of a rough sketch. But how many had something like this for number 37? All right, questions there. All right, number 38. They gave us f of x is equal to negative x squared positive 10x negative 28. What was your standard parabolic form on this one, Kendall?
X minus 5 squared negative 3.
But we lost something.
The negative.
Negative. Okay, so that means there's going to be 3 things we have to do to our parabola this time. What are those 3 things?
The vertical shift down 3.
Down 3.
And then to the right 5.
Forward 5. Right 5.
And then flip.
We're going to flip this over 1, down 1, over 1, down 3, and so on and so forth. We get something like this. If you graphed them together, it'd be close to that. How many had something like that for your second parabola? Presumably on the same graph grid. Ooh, questions. What did we mess up?
Flip.
You forgot to flip? Okay. Questions? Anything else?
I have positive 5 and positive 3.
Oh, okay, so you went inverse here with the forward 5, but you went up 3 instead of down 3.
No,
okay.
I went left 5 and up 3.
Oh, you did all messed up.
I pulled up the negative and I messed it up.
Gotcha. Okay. All right. Questions, comments, anything else? Number 39 says to identify the vertex using the vertex formula. So here, remember, factor out the A, take negative half of B, and find f of that thing, and also determine whether the vertex is a relative minimum or maximum. Number 39, what was your vertex, Maddie? Negative 426, and will it be a minimum or a maximum? It'll be maximum because of the negative, the parabola going downward, the vertex is going to be the highest point or the maximum point on that graph. So negative infinity to 26 would be your range if it had asked for that. Number 40, what was your vertex? Let's come back to Abby.
12, negative 11.
12, negative 11. Is that a relative minimum or relative maximum?
Relative minimum.
It's a relative minimum because the curve's going to go upwards, so the bottom point is the vertex. So your range there would have been negative 11 up to infinity. Again, not graphing either of those. Questions on those? How many have both of those correct? Good on the vertex, good on the min and max. Any questions on 39 and 40? Let's take a look at a couple of word problems then that involved these parabolas. Read number 41 for us, if you would, Audrey.
Elizabeth's flower shop had an increase in sales last month. The sales in hundreds of dollars can be graphed using the equation y equals negative x squared plus 4x plus 3. If the number of customers and tens of customers is the input by the point where the sales reach their maximum, how much did Elizabeth make and how many customers did she have?
All right, when it says sales are reaching their maximum, as far as the parabola goes, the maximum is going to be at the... It's unlocked. Come on in. Welcome back. All right. I'm going to take that from you. So coming back, sorry, Audrey. So we said that the sales are going to be at their maximum where on the parabola? Well, Audrey, let's just think really logically. Where's the maximum point on that thing?
At the top.
What do we call the top?
The max.
And what do we call that?
Vertex.
Vertex! There we go. So when it says where are the sales of the max, all it's asking, class, it's a big fancy way of saying, what's a vertex? That's all we had to do. What did you find the vertex to be on number 41? Genesis?
2, negative 1.
You're right about the 2, but not the negative 1. Michael?
2, 7.
2, 7. Should have been the vertex. Well, remember, it says that the input here, the x, is the number of customers, in tens of customers. So how many customers did Elizabeth's flower shop have at its highest point, class? 20. Because it said tens of customers, so 2 tens would be 20. And then it said the output is the sales in hundreds of dollars. So what's the sales, class? $700. Find the vertex, answer the question. That's all we had to do. Obviously, Abby had it. Anyone else have that? Michael, good. A couple people had that. Questions from those who did not. Let's take a look at number 42. Read that for us, if you would, Maddie.
Donnie Simpson at one point his pet falcon catches its prey, and the falcons dive and feed and represent how y equals x squared negative 2 and x plus 2 negative 2. Determine the point where the falcon catches its prey, and then put this in seconds. How high is the falcon at the point and how long did it travel?
All right, so the input is seconds, the output is feet, and the height of the falcon. And now notice all of our other word problems have involved a negative x squared, right, at the beginning, because all of these have been this kind of problem. Well, the falcon diving is not inverted, so he's actually diving down, and obviously as he dives, he's diving closer and closer and closer to the ground. The question is, how high off the ground is he? That would be your y, or your f of x. And then how many seconds of time does it take to get to that low point where he grabs his prey? But again, we're just finding, class, the vertex, right? Because presumably at the vertex, he grabs food and goes back up. What was the vertex of this particular parabola, Maddie? 5, 1/2 is the vertex. So the question is, how many seconds did it take the falcon to dive, class? 5 seconds. And how high off the ground was he when he snagged the food? 1/2 of a foot. So maybe this is, a little cat or something. And the falcon decided the cat looked like lunch, kind of like the people at the Chinese restaurant. And so you did the dives down, and 6 inches off the ground, he's got cat and makes his getaway. How many had 5, 1/2 for your vertex? All right, questions on that. All right, for those who did not necessarily understand what we were going for on the homework word problems, do you feel like you understand them a little better now? Because we hadn't done a lot of them in class yesterday. Kind of ran out of time. So curious to see how we did. Does it make sense? All right, let's look back then at page 210. And I want you to do number 47. Back to page 210. I want you to do number 47. I've got a World War II thing. right, Michael, go and read word problem 47 for us.
A particular cannon used in the Civil War fired projectiles that followed the parabolic path represented by the equation y equals negative x squared plus 6x plus 12, where x represents feet traveled horizontal and y represents feet vertical. How high were the projectiles fired from this cannon at their highest point?
Again, at their highest point means at the
Vertex.
vertex. So really all you have to do is find the vertex. There's two ways to do it. Again, vertex formula, or you put it in the standard parabolic form, and you can see the HK is your vertex. What is the vertex here?
3 and 21.
3, 21. Now this is really highly unrealistic. The question only asks, what was the height of the projectiles at their highest point? The answer is
21 feet.
21 feet, because the output, but if you really thought about this height of 21, right, that's the highest point on the parabola, but this distance is half the distance, and that's the 3. And that'd be the other 3. So this particular cannon is only firing projectiles how far?
6 feet.
6 feet. Okay, this makes absolutely no sense, but I did not write this word problem. The point they were going, I don't know, this cannon was meant, I don't know, you ever played one of those video games where you fire something basically almost straight up and it comes basically in? That's kind of what this cannon's doing. It's intended to blast the guy sort of like right on the other side of the wall, maybe? Maybe that's what it was. The Union soldiers were on the other side of the wall, and so the Confederates fire the cannon straight up so it comes straight down, basically. Maybe that's what this was. I think it's really unrealistic. But 21 feet is the answer they were looking for, because that's the y value, or the f of x value, I guess in this case y value, of the vertex. How many had 21 feet? All right, and again, just a very unrealistic problem. Turn back to page 608 now. Page 608. At the very back of the book, got some extra exercises here. I think we need maybe a little bit more practice with this. Make sure you are comfortable, confident that you know how to do this. I want you to do problems 11 and 12. 11 and 12, they're on page 608. And we will see how you do with these two. Michael's got them both. If you want to go back up to 9 and 10. For sake of time, let's go and take a look at these. Brandon, if you'll read number 11 for us.
People often throw pennies into a fountain at the mall while it is open from 10 a.m. to 10 p.m. on weekdays. The number of pennies thrown into the fountain follows the
Parabolic
curve. F of x equals negative x squared positive 32x minus 162. Determine the time at which the most pennies are thrown into the fountain. What is the maximum number of pennies thrown at the time?
All right, so x is the time, and then f of x is the number of pennies. I don't know, they don't really have fountains at the mall here, do they? I'm trying to think. I don't think I've ever seen them. Where I grew up, both malls, there were two large malls in Pensacola where I was growing up. Both of them had fountains in them, and of course there were pennies all over in the bottom of them. So I think that's where this got its inspiration. But again, if we're trying to find the peak time, class is asking us to find the vertex. Really straightforward. Okay, so to find the vertex, again, I'm going to factor out the negative, do an x squared plus 32x, minus 32x. I'm going to leave the negative 162 because I like the standard parabolic form more than the vertex formula. I'm going to half class and square 256. And again, calculator can help you with that, but realize it only looks like a 256. It's really a negative 256. So I'm going to have to add a positive 256 to offset. We'll make this the binomial squared class, x minus 16 squared. Then when we combine these together, it gives us a positive 94. All right. Now what this means is that the vertex of my parabola is what point? Coming back to Brandon. 1694. So if x is the peak time, what time do most of the pennies go into the fountain, class?
4 o'clock.
16 o'clock or 4 p.m. So there's the answer to the first part. The second part is how many pennies are going in the fountain at that time, and that answer, of course, is 94 pennies. How many had 4 o'clock p.m. and 94 pennies? Okay, several of us, some of us still not. Questions? Questions? By the way, what if it said, how many pennies at, 2 p.m.? How would I find the number of pennies at 2 p.m.? Well, thinking in terms of time, how would we describe 2 p.m.? 14 o'clock, right? 1400 hours, or 14. So we would find f of 14. At your seats, go and find f of 14. Now it tells us how many pennies are going in the fountain at 2 o'clock. If it had asked for it, it did, but if it had, and I'm not doing that in my head either. 32 times 14.
90.
And yep, so 90 pennies. So not a whole lot more pennies going in at 4, frankly, than at 2, right? But 90 pennies going in the fountain at 2 p.m. Make sense? What if I said how many at 8 p.m.? What would I have to do, class?
F of 8.
Not f of 8.
2.
F of
20.
20. F of 20, right? Would give me how many pennies at 8 p.m. Does that make sense? How you could find different amounts at different times? All right, we're not going to, though, because we're too lazy. Let's take a look at number 12. Read number 12 for us, if you would. Kendall.
A high school baseball player was playing catch with a teammate. On a particular throw, the flight of the baseball followed the parabolic path, represented by y equals negative 116 x squared plus 18x negative 1,251, where x represents feet traveled horizontally and y represents vertical feet. How high will the ball be from its highest point?
Now, this is actually a realistic problem. Okay, that particular parabola is actually realistic for a throw. It's also a lot uglier. Okay, so you see why they've given us such unrealistic parabolas, because they're easier to work with. That thing's a beast. But what do I have to do to start out, class? I've got to factor out a negative 1/16. So when I pull a negative 1/16 out of a negative 1/16 x squared, of course, class, that's easy. That gives me x squared. But here I'm going to take a positive divided by or factored by a negative. I'm going to divide 18 by 1/16. Do we ever divide by a fraction, class? So we're really going to need to multiply by the reciprocal. So it's really 18 times 16 gives me some big number. 288, you like that number? All right, or on your calculator, you could do 18 divided by 1/16. It would give you the same thing. Leave a gap, minus the 1521. And then comes the fun part, where we're really glad we have a calculator, because what do I have to do to the 288 class? Half and square. To get what?
20,736.
That sounds right. 20,736. And now again, it only looks like a 20,736. Really, I've got to multiply that by a negative 1/16 to find its true identity. And it really is a 1,296. So I'm going to put it's a negative 1,296. So I'll put a positive 1,296. And that'll give me a negative 1/16. Quantity squared is going to be an x minus 144. And when I combine here, I end up with a positive 45, it looks like. All right, anyone else get that? All right, so what is the vertex of the parabola going to be?
144.45.
144.45. Remember, this is the height of the throw, and this is the horizontal distance it's traveled to that point. It's traveled 144 feet when it hits that height. So picture this. It's gone up 45 feet to the highest point. That's all it asked for. What was the throw at the highest point? 45 feet. That's pretty realistic. It's traveled 144 feet to get there. How many feet is it going to travel on the back end? Class coming back down.
144.
So what's the total distance of this particular throw?
288.
288 feet. See how, again, it was nasty because of the fraction, but without that fraction, nobody throws a baseball like this. Okay, you don't. Okay, so they had to flatten it, compress it, and invert it, of course, in order to make it look more realistic. They hadn't given you realistic ones up to this point because the math is just messy, but not impossible. How many had the 45-foot height on that throw? Okay, a couple of us did. Those who did it, does it make sense now? I'm going to have you practice a couple of these in your homework this evening. For now, though, we need to move on to your final topic for this section. I told you we've got a test coming up in the not-too-distant future. Last section in your notes. That just broke. That's highly unfortunate. Next section in your notes, rational functions. Rational functions. Anytime we see the word rational, it implies what in algebra class? Fractions. Okay, so these are fraction functions. Rational functions. Some things we talked about earlier when we talked about rational functions, we mentioned that the denominator cannot be 0. I want you to go and jot that in your notes again. The denominator cannot equal 0. Obviously, this is going to limit the domain, remember? We used to say before that if we had a function of x is equal to 2x minus 3 over x plus 4, we would say the domain is all real numbers except class -4. Because a -4 would give you a 0 denominator, and the denominator can't be 0. This is the limit on your domain. And that's not going to change. A couple of things, though, that I want to mention with this is the graph itself. When you graph a rational function, most common rational functions are going to form this curve something like this and a curve something like that. Not a parabola, but two curves. It's referred to as a hyperbola. Most, not all, rational functions will do some sort of hyperbola. What ends up happening here is that the graph will come up to a point and it'll just keep getting higher and higher and higher and higher, closer and closer and closer. For instance, in this case, the way I've got it drawn to the y-axis or the f of x axis. It's going to get closer and closer and closer, but it's never going to touch. This will get closer and closer and closer at the other end of this same line, but never touch. Graphically, we would put a dotted line right here. And this dotted line, this vertical line, is referred to as an asymptote. Asymptote, A-S-Y-M-P-T-O-T-E, silent P. Okay, it doesn't say asymptote, just asymptote. Why is the P in there? To make it a more fun word when you play hangman, because who seriously is going to figure out that word? But anyway, an asymptote. All right? An asymptote is simply a line on a graph that the graph itself approaches but never touches. We had team names years ago for some sort of competition I was doing, and the one team decided to call themselves the Asymptotes, and their slogan was, "You can't touch this." All right? Okay, whatever, that's true. All right, I'll give them that. But the asymptote. And so, for instance, if our domain excludes, as it does in this case, a -4, then we will have a vertical asymptote right where x is -4. There will be an asymptote. And this particular graph will never touch -4. And that's how you can have a single value excluded. For a parabola, right, a parabola would just come down in the reverse course again when it reaches its limit. Here, the limit is just a single number, not a whole range of values. And so that's how it'd be accomplished with an asymptote. Pretty easy to find vertical asymptotes. See what x can't be. That's where your vertical asymptote will be. It is possible to have more than one asymptote. Look at page 211. Look at page 211. And I was on the wrong page completely. Look at page 211. You see, by the way, a sketch, a computer-generated sketch here, and it sure looks like that graph is hitting that y-axis, but not quite. If you zoomed in closer, you'd see it's still not quite touching. Notice there's also a horizontal asymptote. We're going to get to that in just a moment. We see that term there as well for you in bold. Look at the next page. Look at the next page, page 212. Look at the example problems. In example 4.9a, look at your denominator there. I believe it's a 2x plus 4. Is that correct in your denominator? Okay, mine originally had 2x minus 4. I have a little edit in my book. I was making sure yours is correct. All right, so 2x plus 4 is the denominator. It says find the vertical asymptote. Well, pretty straightforward. They set it equal to 0, or I would say unequal to 0. And they found that x cannot be -2. So that's where your vertical asymptote would be. Easy enough? Notice, first power in the denominator, one asymptote. Look at example B. Look at your denominator. It's an x squared minus 9. When you set that unequal, again, I would say unequal to 0, you're going to get that x cannot equal 3 or -3. That particular graph would have an asymptote at the 3 and an asymptote at -3. And so what you might end up producing is some weird shape like this. Okay, the asymptotes kind of cut it off into 3 sections of the graph there. Questions on that? All right, so as you turn to page 217, with rational functions, for the first time in your life, you see asymptotes. We're just focused on the vertical asymptotes for now. I want you to find what would be the vertical asymptote or vertical asymptotes for each of the functions 1 through 6 on page 217. And anywhere that the denominator would equal 0, that's where the asymptotes will be, since the denominator cannot equal 0. Set the denominator unequal to 0. That'll tell you where the asymptotes go. We're literally just going to say this can't be 0.
Okay.
What value right there would give you 0? That's your asymptote. That's all we have to do. Yeah, that easy. Yep. Again, if the denominator is quadratic, you're expecting 2 vertical asymptotes. So you have a little mini quadratic equation there at the bottom. Pencils down, even if you're not finished. Number one, the denominator. I don't care about the numerator right now. I just care about the denominator. It says x plus 8. If I set that unequal to 0, class x cannot equal negative 8, then that's where my asymptote is. My asymptote is going to be at negative 8 on the x-axis. Makes sense? How many had negative 8? All right, look at the next one. We have a 2x positive 9 in the denominator. Again, set that unequal to 0. What can x not equal, class? Negative 9, when you move it over, and then divide by 2, negative 9 halves, or negative 4 1/2. Okay, so obviously that'd be between the negative 4 and negative 3. That's where my asymptote is going to be. How many had the negative 9 halves as your vertical asymptote? Number 3, it looks confusing and it wants to throw you off, but realize for this to equal 0, you'd have to take the square root of what? 0. So really all you care about is that x plus 1 can't be 0. Does that make sense? What value for x can you not have then? A negative 1, because a negative 1 would give you 0, square root of 0 is 0, you can't have that. Or you could say, square both sides of this inequality. Square a square root, you get the radicand. Square of 0, you still got 0. Basically, the radicands just can't be 0. Does that make sense? So don't overthink the radical there. X just can't be negative 1. There's your asymptote at negative 1. So on number 4, it's the 2x plus 2 specifically that can't equal 0. I know it's in a radical, but it's still the 2x plus 2 that can't be 0. So class, x cannot be negative 1. Subtract away the 2, divide away the 2. X can't be negative 1, so same asymptote as the last time. Does that make sense? Number 5, there's going to be 2 asymptotes. Because the x squared minus 5x minus 14 can't equal 0. What am I going to have to do to this quadratic trinomial, Genesis? Factor it. Yeah, when we factor it, we end up getting what, anyone?
X minus 7x plus 2.
The x minus 7x plus 2. So what two things is x not able to equal? 7 and negative 2. So 2 asymptotes here. One will be at negative 2. The other will be at positive 7 on that particular one. How many had 7 and negative 2 for your 2 asymptotes? All right, very similar problem. On number 6, what are the asymptotes going to be? Again, the vertical asymptotes going to be on number 6. Audrey?
Negative 8 and 3.
Negative 8 and positive 3. Questions on those? All right, do we understand a little better now that you had a chance to try it on your own? Was anyone perfect? You managed to get them all. Not bothered if you weren't, but okay. And those who didn't get them all, we understand it now? That's vertical asymptotes. But remember, if you flip back to page 211 it was? Page 211, we could also have horizontal asymptotes because we have to split this thing not only up into a vertical division, but there's also going to be a horizontal division. Of course, what you see pictured is the axes here functioning as your asymptotes. There's a limitation on the range. Now, if we go back to the thing that I erased a second ago, remember we said that the limitation on the range, maybe it was something like 2x minus 3. So let's just go back to this function here. We said the limitation on the domain was denominator can't be 0. X is all real numbers except negative 8. What did we say we would do for the range on a rational function, class? Divide the leading coefficients, here 2 and 1, and we said the range would be all real numbers except, in this case, 2. And I told you that's partially true. That was true of all the ones they gave you then. but there's actually 4 different ways to calculate horizontal asymptotes. So next thing in your notes, under this rational function thing, horizontal asymptotes. Horizontal asymptotes. And remember, this is what's going to limit the range. 4 things. It does have to do with the powers in the numerator and the power of x that you've got present in the denominator. First of all, if the degree, that refers to the total sum of the powers in the highest term, if the degree of the numerator is less than the degree of the denominator, that is, you've got a bigger x in the bottom than you do in the top, like a squared in the bottom and just a first in the top. Or you've got like a 5th power in the bottom and a cube in the top. If the numerator's degree is smaller than the denominator's degree, then f of x cannot equal 0. In other words, the x-axis is your asymptote. And that's what we saw in that example just a moment ago on page 211. I think most of you are still there. In that particular function, the x-axis is your horizontal asymptote because the numerator's degree is smaller than the denominator's. This is going to be the most common thing that we will see, is a higher power in the bottom than in the top. In fact, that's what we saw on many of these problems we just worked there on page 217. Another thing that we will occasionally see is if the degree of the numerator equals the degree of the denominator. This is actually what we saw in the last section when we first talked about domain and range. They were always equal. Did you notice that? It was always first power x in the top, first power x in the bottom. Well, if that's true, then f of x cannot equal the ratio of leading coefficients. So because they always gave you matching first powers in top and bottom, they could tell you it's the ratio of leading coefficients, but that's technically only true if the numerator and denominator powers of x match. Does that make sense? Well, the numerator's degree could be smaller, it could be equal, or it could be greater. I'm going to abbreviate DEG for degree. If the degree of the numerator is greater than the degree of the denominator by exactly 1. Meaning, if you've got a 4th power on the bottom, you've got a 5th power on the top. If you have square on the bottom, it's cubed on the top. You have exactly 1 power bigger in the top than you do in the bottom. We're going to get a weird slant asymptote. We're going to look at that in just a moment. We're going to get a weird slant asymptote. It's not actually going to be horizontal. It's going to be at an angle. You're not going to actually have to graph those. That's college level. All right? For our purposes, just know it's going to be a slant asymptote if that happened. And then finally, it's also possible the numerator could be more than just 1 degree bigger. You could have, for instance, cube in the top, first power in the bottom. You could have 5th power in the top, squared in the bottom, okay? If the degree of the numerator is greater than the degree of the denominator by more than 1, you have no horizontal asymptotes. There are no horizontal asymptotes. Only the vertical asymptotes, which creates a particularly strange looking graph. All right, but anyway, look at page 213 in your books now. Page 213 in your textbooks. We see on page 212 at the bottom, kind of across the page there's your x-axis horizontal asymptote. That's normally what we'll see. You see an adjusted horizontal asymptote at the top of page 213, right? There you have matching degrees. They're both first power x's in the function g of x. So 3 to 1 is 3. 3 is where your horizontal asymptote runs. Do we see that? You're looking in your textbook at page 213. At the top of page 213. Do you see the horizontal asymptote at 3? Okay? That's your limitation of x or y, f of x, g of x is all real numbers except 3. There's that asymptote. In the next example, h of x, you see there's a bigger power in the top than there is in the bottom by exactly 1 degree, squared over first. So we have the weird slant asymptote that just does strange things. And of course, they don't show you an example of the other where there is no asymptote because there's really nothing to show then. As far as that goes, you see that table at the bottom of page 213. That says everything we just said here. Okay, kind of a Cliff Notes version on the board. All right, so look at the example problem on page 214 now. Look at the example problem on page 214. Obviously, if we were finding vertical asymptotes, class, we would say positive negative 3. You see it? Because the denominator not equal to 0, positive and negative 3, so 2 vertical asymptotes. But what about the horizontal asymptote? How does the numerator compare to the denominator's degree? Numerator's less. The numerator's degree is 0. There are no x's. Denominator has 2 of them. Denominator's bigger. If numerator is smaller than denominator, what's my only horizontal asymptote? The x-axis. F of x can't be 0, right? So that x-axis is your asymptote. Look at the next example. On part B, notice they have the same degree. Now, they're still both positive, negative 3 vertical asymptotes, but horizontally, they have the same degree. They're matching. So now my horizontal asymptote is going to be based on the ratio of the leading coefficients. Where's my horizontal asymptote in part B? Are you looking in your textbook at page 214? Part B. Do you see that the ratio of the leading coefficients is 4 to 1, or 4? That's your asymptote. So if I were graphing this, I'd find 4 on the y-axis and put my asymptote there. Look at letter C. Notice this time the numerator has a second power in it. The numerator, or denominator rather, only has first power. Who wins? And if the numerator wins by exactly 1, it's going to get a slant asymptote. What is it? Don't worry about it. It's just a slant asymptote. We're not going to stress over the other. Questions on how this applies? All right, we're running out of time, so we're going to have to give you this for homework instead of classwork, and that's page 217, 7 to 12. We're going to look at it tomorrow, or rather in our next lesson. Page 217, numbers 7 through 12. We'll look at it in our next lesson. Get some sleep this weekend. Have your brains ready to go, because we do have a test coming up on Wednesday. Lesson number, 118, I think is what I said yesterday. Lesson 118, test coming up Wednesday. We'll wrap up these asymptotes and rational functions, how to graph them. Do a lot more of that Monday than Tuesday, reviewing Wednesday. Your test over sections 4.6 to 4.9. All right, have a wonderful rest of your day, and you are dismissed.